Leave a block of ice on a counter at room temperature, and it melts entirely on its own. But a puddle of water will never spontaneously freeze unless you actively put it in a freezer and run a compressor. One direction happens naturally, the reverse requires external effort. To understand exactly why, we use thermodynamics, the rigorous accounting of mass, heat, and energy. Before we track a single joule of energy, we have to define exactly what we are tracking. In any equation, the specific region we are studying is called the system. Everything else around it is the surroundings. Added together, they make up the universe. This animated diagram shows how we classify systems by what they allow across their borders. An open system, like the open beaker, exchanges both mass and heat energy with its surroundings. A closed system, like the corked flask, traps mass inside but still lets heat flow in and out. An isolated system, like the thermos, completely blocks both heat and mass from crossing the boundary. Within those boundaries, we measure two types of properties. Intensive properties, like temperature, pressure, or density, are independent of the system's size. A single water droplet and a massive ocean can both sit at exactly 25 degrees Celsius. Extensive properties, however, depend entirely on the amount of matter present, meaning the ocean's total mass and volume will be drastically larger than the droplets. This 2D schematic of a mountain shows how we evaluate changes in a system. If a climber moves from the base to the summit, their change in altitude relies solely on their starting and ending points. In thermodynamics, properties like this are called state functions. However, the actual physical distance they hike to get there depends entirely on the route they chose. Variables tied to the route, like the heat transferred or the work done, are called path functions. Setting strict boundaries and defining exactly how we travel between states is the only way to accurately track energy transfers without making critical accounting errors. The first law of thermodynamics states that energy cannot be created or destroyed. We track this using internal energy, or delta U, which is the sum of the heat added and the work done. This graphic represents our system as a wallet. The internal energy is the total cash inside, and there are only two ways to change that balance: heat, represented by Q, and work, represented by W. Heat is simply energy currency flowing due to temperature differences. When heat flows into the system, an endothermic process, we assign Q a positive sign. It is a deposit. When heat flows out of the system into the surroundings, an exothermic process, Q gets a negative sign, acting as a withdrawal. Work usually involves gases expanding or contracting. When the surroundings compress the gas, work is done on the system, meaning energy is deposited, making W positive. But when our system gas expands against external pressure, it is doing the work. It spends its own energy to push out, making W negative. We calculate work using two primary equations. For an irreversible process against constant external pressure, work equals negative P external times the change in volume. But if the gas expands isothermally and reversibly in infinite tiny steps, work equals negative 2.303 nRT times the log of the final volume over the initial volume. Notice that both equations carry a negative sign. Memorizing this wallet sign convention is your primary defense against completely reversing the math in a first law calculation. Because most real-world chemistry happens in open flasks under constant atmospheric pressure, gases can expand and do work. To account for this conveniently, we use enthalpy, represented by H, which equals internal energy plus pressure times volume. For a reaction involving gases, the change in enthalpy equals delta U plus the change in moles of gas times RT. This animated equation shows Hess's law. Because enthalpy is a state function, the total enthalpy of a reaction is the same whether it happens in one step or ken. To find it, you add up the standard enthalpies of formation for all your products and subtract the sum of your reactants, products minus reactants. But we can also calculate reaction enthalpy using bond energies, the energy required to break bonds in the gaseous state. Breaking bonds consumes energy, while forming bonds releases it. So here, the equation is the sum of bonds broken in the reactants minus the sum of bonds formed in the products. Pay close attention to the order of subtraction. Hess's law subtracts reactants from products, but bond enthalpy requires the exact opposite. The energy of formed bonds is subtracted from the energy of the bonds broken in the reactants. Reversing this order is the primary reason students arrive at the wrong sign for their final enthalpy, leading to incorrect predictions about whether a reaction is exothermic or endothermic. The first law balances the energy, but it cannot tell us if a reaction will actually happen on its own. For that, we need entropy, represented by S, which measures the degree of randomness or disorder in a system. The second law of thermodynamics dictates that for any spontaneous process, the total entropy of the universe must increase. This empty 2x2 grid is our spontaneity table, governed by the master equation for Gibbs free energy. Delta G equals delta H minus T delta S. By combining the heat of the system with the disorder of the system at a specific temperature, Gibbs free energy definitively predicts reaction spontaneity. The math gives us absolute rules. If a reaction releases heat, making delta H negative, and increases disorder, making delta S positive, delta G will always be negative. The reaction is always spontaneous. Conversely, if a reaction consumes heat and decreases disorder, delta G is positive. It is never spontaneous. The conditions change when the signs match. If a reaction is exothermic but creates order, the negative delta H drives spontaneity, meaning it only works at low temperatures. If a reaction is endothermic but creates chaos, the positive delta S takes over, meaning it requires high temperatures to become spontaneous. We can also link the standard Gibbs free energy directly to the equilibrium constant, K, with the equation delta G standard equals negative 2.303 RT log K. By combining enthalpy and entropy into one calculation, the Gibbs equation provides the final numerical sign needed to determine if a reaction is physically capable of occurring in the real world. Let's lock this logic in. Pause the video and predict. If a reaction is endothermic, but it significantly increases the entropy of the system, what temperature condition is required to make it spontaneous? To make a positive delta H overcome a positive delta S and yield a negative Gibbs free energy, you need high temperatures to scale up the entropy term. This static vector graphic lists all 8 core formulas we've covered. Screenshot this frame. You will need it to solve the vast majority of problems in your class. Now, test your conceptual understanding. Answer Part A in the comments below. Explain why free expansion in a vacuum yields zero work. Classify intensive versus extensive properties, and predict the sign of entropy when a gas condenses into a liquid. Then tackle the numerical problems in Part B. Calculate the change in internal energy when heat is absorbed and work is done by the system. Run the delta H conversion for a gaseous reaction, and calculate reversible isothermal work. Thermodynamics can feel abstract at first, but mastering these specific variables and their sign conventions turns the complex movement of the universe into simple, foolproof energy accounting.